Hello everybody, welcome back to our calculus examination preparation course. In today's lecture, we're going to continue our differentiation topic. And I'm sure that you will be very excited because we're going to calculate. Alright, so let's continue about the limit properties. We talked about the uniqueness property last time, and this time we're going to talk about the locally bounded property. So what is it? Well, the definition about this theory is, so if there's a limit, right, for the function f(x), so when x approaches to x0, f(x) approaches to a. So it means there's always exists a positive number n. So when you choose x in this range, from 0 to delta x, which means you're in the neighborhood of x0, right? Neighborhood of x0, and the range is about 0 to delta x. So there's always means the f(x) absolute value is smaller than n, which means the f(x) is also bounded. Okay, let's look at this on the function graph here. Now we have this function f(x). Okay, so it means if we have a limit here, like this one is called a. Okay, it's called a around at the point x0. So it means if we choose the neighborhood of x0, right? Defined by the formula here. Okay, this is like x0 minus delta. This is like x0 plus delta. So in this region, now we have the f(x) in this region. So for example, we can say the f(x) equals to maybe 5 here and 7 here, right? So it means if n equals to 8 or anything which is a little bigger than 7, now we can say f(x) absolute value of it is smaller than 8. So it means, it is correct because on this point it is 5, on this point is 7, and now on this point is even lower than 5. So we can say that the function's value is also within a certain range. So we can say it is locally bounded. Locally bounded. Okay, so how can we prove this? Inverse trigonometry functions. And please, take a little time, maybe just 2 minutes to remember these, like the cotangent sin x derivative equals to the 1 over the square root of 1 minus sine x squared. Now these are very important later for us, especially for the integration. Integration is much harder compared to the differentiation, which is relatively simpler. Okay, and for the final group we have this. Well, this one is very useful too. And if you want to prove them, for you to help you to remember them, no problem. You can simply find out the derivative of the line x plus the square root of x squared plus 1, and you will find out that after a long deduction, you will find out the simple form of the derivative. Yeah, surprised, right? The derivative of this complex formula is actually much simpler. And also similarly, if you change x squared plus 1 to this x squared minus 1, you don't have to do anything special. Just put a minus sign here. Okay? Alrighty, so please, take some time to remember this. This one is important. Okay, so next we're going to talk about the derivative operations. So As we understand that, we have the basic algebra operations: addition, subtraction, multiplication, and division, right? So this similarly in the differentiation about the two functions. Now we have the function u and function v here. So if you want to do the plus or the minus operations, so it is very simple. You just find out the derivatives of each function and put them together. So this is very simple. But if you want to do the multiplication about the two functions, so here we just like for u, okay, we found out its derivative first, and have the function v left alone. You don't have to do anything with it first, and then plus the u, okay, well, times the derivative of the function v. So we can deduct from this. Now you can see that if we have let's have the u, v, w, we have three functions. So now for its derivative, well, simply we'll have u, vw, and u, vw, and u, vw. Yeah, just trying to find out the derivative of each item for a single term, and then add all the terms together. Well, this one is very simple for you to prove. I will give you some hint here. So for u, vw, okay, so we understand that there is the association law. Okay, so we can look the three function multiplication as vw, okay, like this, right? So now we can follow the the two the two items multiplication derivative case. So we can have this one and have this and have this one and have this, right? Okay, so now you can further apply the two item multiplication rule into the parentheses. So we're gonna have u, vw, u, vw, and vw, and then you can multiply the u into the parentheses. See, now this one has been approved. Okay, so this is about the three items multiplied together. So how about the n items? Well, this is very u1, u2, all the way to un. What about this? Yes, and from those two items and three items multiplication case, you can simply generalize the rule as u1, u2 to the way to un plus u1, u2 derivative all the way to un, and then u1, u2, and all the way to un derivative. Got it? Okay, so we're gonna apply this rule to our future derivative calculation later. Okay, so for the division, it's gonna be a little harder. So for division, like u divided by v, okay, so its derivative equals to the denominator v squared. Okay, don't forget about the square. And on top, it's similar to the multiplication. It's u prime. U prime means the derivative of u. I would just say u prime for short. Well, times v, and u times the v prime. Well, but we have to change the plus sign to the minus sign. That's it. So this is the very basic, derivative operations. We're gonna use them a lot later. Okay. So next, we're gonna talk about the basic derivative methods. So the first one is about the compound function's derivative. Compound function looks like this. So you have function fx, but your invariant variant here is not simple just x or some other letter, but another function. For example, gx. So this time, if you want to find out, the derivative of, f gx, okay, so we simply have to, okay, find out this whole thing, okay. So have to find out, the derivative of, f x first, and put a gx in, and then find out the gx's derivative. That sounds kind of abstract. Let's look at one simple example. For example, we have sine 2x. So we understand from the basic derivative table that, while sine x's derivative is very simple, which is cosine x. However, here we change this, the x within a sine x into 2x. Okay, so our fx is sine x, and our gx will be 2x. So we have to find out our fx first. Of course, it is cosine x, but we have to, put the gx in. Okay, so that's why we have to put the 2x in. So we're going to have cosine 2x. And then we have to find out the derivative of the gx. In our case, it's the 2x. And its derivative is 2. Very simple, right? So finally, we just put the 2 on the front. So it becomes 2 cosine 2x. Alright, I understand that some students are so good at math or want to learn more. I understand that, well, this case is too simple. And in our applications, like if you're studying physics or economics or the electrical engineering, you're gonna meet some function derivative operations which looks more complex. So here, how about we try something more challenging? So here we have, this is example 1, I would say this is example 2. So we have a function, looks like this. Okay, and of course I have to say the range of x is, bigger than 0. Okay, so find out the derivative of y. Wow. Well, I think most of the students will be like very scared. So, this one looks so complex, this part. And this one, look, we never have such functions before. It does not look like a power function, it does not look like an exponential function, but looks like a combination or mixture of them. Yes. So we don't have the derivative formula for this, as you could find in that table we just shown before. However, we can change it to something we're familiar with. Okay, so let's change it to y equals to e 2x line x. Do you understand how it happens? Okay, let me show you some details. So for this one, x is the base, and 2 to the power of x as the power. So we can, change this one to this. Right? You can verify it. So, this one and this one are the anti-operations. So finally, we still get this, correct? But the function for this is, for the line operation, we can simplify the power while to the multiplication. Okay, so that's why we're going to have e, well, the 2x x. Yes, that is something we're familiar with. This part has been converted to an exponential function, and this one has been turned into a line function. Easier. Okay, so similarly, we can do the same thing to the second item for the function we have here. So we're going to have ex line x. Alrighty, so the next item, well, it is not that complex actually. Don't be scared by its form. So we understand that the square root of x, right, equals to the x to the power of 1 over 2. Okay, So let's see. So this one. Okay. Well, let's put the the root square root operation to each item within. So we're gonna have this one, and sorry, and this one. Okay. Okay. So much simpler, right? So you can have this, and the final result is gonna be x. Right. Okay, so if you still have trouble with this basic, power operations, you have to go back to your middle school or high school algebra courses, to find out the corresponding chapter and read that chapter carefully. Alrighty, so now let's find out the derivative of y. Alright, so for the first item, so it's a compound function. So the first, the outside derivative will become the something within our basic derivative table. It's about the exponential derivative. So it's going to become something like this. Well, and this can be, actually put back as its original form. This one, original form. Okay, so let's put it back to save the space on the paper. So it's gonna be this. Okay, now we have to find out the g-axis derivative. Okay, the g-axis here means this. Okay, and we understand that it's about the multiplication derivative. So we have to find out, this and this respectively, like, okay, line x and plus this one, x. Okay, so further we can have Alrighty, so by now we have find out, the first item's derivative, okay? So now our job is to find out the second item's derivative. So the second item's is about this. And follow the similar route, we can have it written down as okay, and finally the third item. Okay, so of course, for the third item it's much simpler. So we can follow the compound derivative rule and write it down as Alrighty, so that's the end of the solution. And you can see that, we got a very complex derivative expression. Alrighty, hopefully you understand the compound function derivative operation. If you got it, let's look at something more challenging. It's called the implicit functions derivative. So usually, we have the basic regular function as y equals to expression about the x. For example, y equals to 2x. This is very simple. We understand how x is related to y by this analytical expression. However, for our implicit function, we usually have something like this. You're going to have an equation. And you understand that from this equation, you must have, it contains something like this. X and Y does have a connection. However, you just cannot find, the regular expression about X and Y like that. So this time, we have to, do the derivative operation on both sides. Both sides, of the equation. Okay, both sides of the equation to find out the expression for the y's derivative. Well, I understand that this sounds very abstract. So why don't we look at one specific question? Okay, here we go. So I will let it to be like this. Well, I want to find out the second order of the function yx. It does not look that complex, does it? Well, we will see. Alright, let's start. So we do the derivative operation on both sides of this equation. So let's do this. Y, okay. Okay, and then we have do the derivative operation, in each item, for each item in the parentheses. So of course, one's derivative will be 0, so we don't have to consider it. So for this guy, we just have to take it as the multiplication's derivative, and let's do it. Okay, and we can further write it down as, because x's derivative would be 1, so we only have the e to the power of y left. Okay, so on this side, we understand that we can simply, write it down like this. However, y is a function of x. So this one, e to the power of y, is actually a compound function. So that's why we have to add this one here. Got it? Well, if you look confused, please review the compound functions derivative section. Alrighty. So now we understand that on the left and on the right of the equation, we have the y prime. So why don't we simplify them a little bit? We can, put this on the left. So we're going to have y prime minus x exponential. Oh, put to the wrong position. Okay, like this. And on the right we have, so we're going to have y prime extracted ey. Okay, and finally we can deduct y prime equals to ey divided by e to the power of y times x. Well, you can take this form, but if you want, you can further do something on it. From our observation, it seems like, this form and this form is very close. So we can do some equivalent conversion here. So we're gonna, change the x times e to the power of y plus 1. Of course, on the here we're gonna have 2. Yeah, we'll get the same result. However, we can change this whole thing to y. Okay, got it. So this one, maybe in most people's eyes, will look much simpler. Alrighty, so let's put a y prime here. The final result for the I prime, or to say the first order derivative, is this. Or you can just put this guy in as the y prime too. It doesn't matter. Okay, so since we have to find out the second order derivative, we have to do it, on both sides of this equation. Okay, put it like, okay, this whole thing, and we have this. Okay, this is about the second order derivative. Okay, don't be scared about its form. It's still about, do the derivative operation on each item inside our parentheses. Okay, so the first one is about this item's derivative and this guy. The second derivative is about this guy. Okay, this guy is very simple. So it's an exponential function. We can simply write it down as what it is. But don't forget, because y is actually a function of x, so this is actually a compound function's derivative. So we have to add the y's prime here. Okay. Okay, so we understand that, for in this one, we actually have, 1, 2, and 3 items within. So remember, this is about 3 terms multiplication. And we simply have to do the derivative on each term inside. Okay, so x prime times the e y and y prime, plus the x times the ey's prime, and then y prime, and then x times e to the power of y and times the y prime's prime. Okay, so here, this one is very simple, right? We can just get rid of it. So we're going to have ey y prime. Okay, for this one, remember, this is still about the compound function's derivative. So we can have something like this. Okay, so we have 2 y's primes here. So we're going to put it like this. And for this one, okay, so we had e to the power of y, and then y prime's prime will give us the second order derivative of y. So we're going to do the y prime prime. Okay, so now we have finished most of the calculation part of the y's derivative. So we can say the y's second order derivative will become something like this. However, if you want to make the y second order derivative more, distant, like, we have this here, we have this here, so that we can simplify a little bit. So you can put the y second order derivative on the left. So we're going to have, 1 minus e to the power of y x. Okay, so on the right, we're going to have okay, so finally, you can simplify this further as y well, since we understand that, the first 2 items look the same, so we can just put them together as this. And also, similar to the final operation to the first order derivative we have now, because the denominator, it's very similar, to our, original expression about y. Okay, so this one. So we can remember, we can just simplify it by this. So we can just put the derivative, the denominator as 2 minus y. Okay, so on the top, if you want to put the result of the y prime in. So here we have the y prime, the e with the exponential as y, and divided by 2 minus y, right? So we can replace every y first order derivative by our first step result. Okay. Okay, so if we want to further simplify this, as we have, the y minus y as the denominator on the numerator position. So if we want to follow the habit, you can simplify, well, this further. So you can well, to the reduction of fractions to the same denominator. So finally, we're gonna have, this. Okay, so this is like a little practice for you. See if you can do it.